Dear students, today we are going to deal with the bounded monotonic sequences. In the last class, we have studied a very important theorem, that is a squeeze theorem, and also we have done a problem related to that. So in this class, next we are going to study another property of the sequences, right? That is bounded monotonic sequences. So first of all, we are going to deal with what do you mean by a monotonic sequence, right? And in this video, I like to explain these things, the increasing monotonic sequences. In the monotonic sequences, I'm included increasing sequence, decreasing sequence, and the problem related to this too. And next is the bounded sequence and the problem related to that, and very important theorem, that is monotone convergence theorem for the sequences. Statement you have to study, and the proof is omitted. And one more example related to this monotone convergence theorem and bounded sequences. These things in this video I like to discuss about these things. All right. First of all, I like to start with a monotonic sequence. And what is the definition of the monotonic sequence? Look at this definition. Monotonic sequence, a sequence, consider the sequence AN. AN is an monotonic means, the word monotonic means it is either increasing or decreasing. Alright. So a sequence AN is increasing if A1 less than A2 less than A3, etc. less than AN less than AN plus 1, etc. Okay, that is, it is increasing if each term is increasing term by term. Okay, and what about the decreasing sequences? Decreasing means if the first term is the highest one, next each term is decreasing one by one. That is, A1 is greater than A2, greater than A3, greater than etc., greater than AN, greater than AN plus 1, etc. This is said to be a decreasing sequence, and this is said to be an increasing sequence. Okay. Next example, we have to show that the sequence n divided by n plus 1 is increasing. N divided by n plus 1 is increasing. Okay. In this textbook, we can use so many methods to show that the sequence is increasing. In this textbook, they have done that AN is equal to n divided by n plus 1. Right? N divided by n plus 1. We have to show that in order to show this is increasing, we have to show that AN is less than or equal to AN plus 1. AN is strictly less than AN plus 1 means it is strictly less than AN plus 1 means it is strictly increasing. Otherwise, it is increasing. Right? We have to show that AN is less than or equal to AN plus 1 for all n greater than or equal to 1. That is, we have to show that AN, here we start from what we have to prove. Right? What to prove? AN is less than or equal to AN plus 1. So first of all, we assumed that relation and start from that relation. What we have to prove? AN less than or equal to AN plus 1 for all n greater than or equal to 1. First of all, we have assumed this condition. Listen. N by n plus 1, which is less than or equal to n plus 1 divided by, this is AN plus 1. AN plus 1 means replace the n by n plus 1. So this is n plus 1 divided by n plus 1 plus 1. So n by n plus 1 less than or equal to n plus 1 divided by n plus 2. right? So to show that this inequality is true, we have to you have to simplify this, cross multiply the both n into n plus 1 or equal to n plus 1 into n plus 1. Expand this. By solving, we can see that 0 is less than or equal to 1. That means our assumption is correct. So, assumption is correct means what? An is less than or equal to an plus 1. So that the sequence an is increasing. So that sequence an is increasing. And also one more solution we can do that. We can do this. Okay. We can do one more solution, that is, we have considered f of x equal to f of n equal to here n divided by n plus 1. I can replace this as f of x equal to, for the easiness only, I'm replaced to this n by x divided by x plus 1. So next I like to take f dash x, that's equal to x plus 1 into derivative of x1 minus x into derivative of this is 1 divided by x plus 1 whole square, which is equal to 1 divided by x plus 1 whole square. Always greater than 0. Which is always greater than 0. That means f of x is increasing for all x greater than 0, which implies f of x is increasing on 0 infinity. On 0 infinity. In this way also we can solve this very easily, right? And next we have to do is we have to show that the sequence n divided by e raised to n is decreasing. We have to show an is less than or equal to an is greater than or equal to an plus 1. An is greater than or equal to an plus 1 for all n greater than or equal to 1. So here we have to do is an is equal to n divided by e raised to n, which is greater than or equal to n plus 1 divided by e raised to n plus 1, which is same as what? N plus 1 divided by e raised to n into e. So this is ne greater than or equal to n plus 1, e raised to n getting cancelled, and this is n into e minus 1, which is greater than or equal to 1. Greater than or equal to 1 is true or not? E minus 1, e is 2 point something minus 1, that is 1.7 into n. N is always greater than or equal to 1. So this is always greater than or equal to 1. This is true. So this assumption is okay. That is correct. So like this we can do the problem very easily. So the sequence is decreasing. Okay. So the first two definitions, increasing sequence and decreasing sequence, we have done that, right? And also we have done two problems. Next is, what do you mean by a bounded sequences? Bounded means what? It is bounded actually means bounded about two types of sequence, two types of bounded sequences, bounded above and bounded below. Bounded above and bounded below. Okay. Bounded above means n is less than or equal to m for all n greater than or equal to 1. an is less than or equal to m for all n greater than or equal to 1. Bounded above means the sequence an must have a bounded value m. And bounded below means in the left side there will be a value such that m is less than or equal to a, and that is a n is always greater than or equal to that value. A sequence is bounded if it is both bounded above and bounded below. If it is both bounded above and bounded below. Okay. Next is very important theorem, and we have omitted the proof also. Monotone convergence theorem for sequences. Monotone convergence theorem for sequences. The theorem says that the theorem is based on the boundedness and monotonicity of the function of the sequence. So every bounded monotonic sequence is convergent. The theorem says that every bounded monotonic sequence is convergent. Okay, we can do the problem in the next class, right? In this class, we have done the decreasing sequences, and bounded sequences means bounded above and bounded below, and very important theorem statement, monotone convergence theorem. That is, every bounded monotonic sequence is convergent. Right? We can do the problems in the next class. Okay, thank you.